Hello and welcome to this long overdue video about logistics in screeps. In this video, I'm going to introduce the idea of logistics and what it refers to, and then I'm going to go through how I approached solving it. To be clear, I'm not advocating that what I've done is the best possible solution. It's just potentially to give you an idea to help you along your journey. I'll also introduce a framework for how I tested it, and I'll introduce the idea of simulations and why they're good as well, and I'll show you some of the results from mine. So, what is logistics and what approaches do people have in screeps? So, very simply, logistics is moving some stuff from A to B using creeps most of the time. This could be, for example, moving stuff or moving energy, from a source to your storage, refilling extensions, looking after your labs. It all falls under the umbrella of logistics. There are two main approaches, and truth be told, most people will be somewhere on a spectrum between these. The first is dedicated haulers. These haulers have one job. So, for example, it could be a lab filler. Its job is to move stuff between the labs and the storage, or maybe a dedicated haulers for a particular source, so they go only to that source and back to storage, for example. The other approach is a pool of haulers. So this is you have some trucks or logistics creeps, whatever you want to call them, and they can actually fulfill any role. So at one moment they might be picking up from a source, then they might swap to filling extensions. And like I said, a lot of people will have approaches that vary on the spectrum between these. Me personally, I go with a full pool of haulers, and I'll be talking about that a bit later. But first of all, what are some of the pros and cons of using dedicated haulers? Now, one of the biggest pros is you're less likely to forget a job. So if you have a pool, you can imagine, it might do one job or another job, and certain jobs might actually get left off. Maybe they're too far away, or maybe they just end up at a lower priority, so they get ignored. It's a lot easier to implement because, it's hauler go there, hauler come back, but it may also be inefficient. This is because, for example, you can imagine like a hauler that's picked up energy from a source. On its way to the storage it's dedicated to, it might pass extensions that could be refilled, but it might not do that because its job is just to take it to the source, which is less efficient, of course, compared to if it actually swapped to filling extensions, as just one very trivial example. It generally lacks flexibility as well. So, for example, let's say all of a sudden it's more important for haulers to do one job. If they're dedicated to only a specific job, they can't very easily swap to fulfilling this more important demand. The opposite end, the very extreme, is pooling. So pooling is flexible, obviously, because each hauler can do every job. It's efficient because, it might fill jobs as it's traveling to wherever, but it's also harder to implement well, to be clear. It's very easy to make a very bad implementation of pooling, and a poor implementation can mean things like jobs get ignored, or actually it could end up being less efficient because you're traveling to more distant jobs when you could fulfill closer ones, for example. So I'm not going to talk too much about this, but I feel like it was very important to mention this just as an aside, which is relaying. Relaying is primarily something you'll see in speedruns. This is because it tends to involve lots of really small creeps, which of course is more CPU intensive. The basic idea is you have one creep that passes its resources to another creep, and then also on the same tick makes a move. This basically means that you get to move those resources an extra tile in a tick, and it means that your speed of hauling from A to B ends up being faster, so you have a higher throughput compared to if you weren't relaying. But again, it usually involves lots of smaller creeps, so you tend to find it more in speed running than you do in world, although of course there are examples of players doing that. So with regards to pooling, where one hauler can do all of these different jobs, how we set the route, like which jobs it should go to in what order, between like a pool of haulers, it's called the multi-vehicle routing problem. And it's actually an NP hard problem, which means it's very difficult, if not impossible, to solve it exactly in screeps. So don't worry, if you're struggling with this, because it's something you just got to make a good approximation for. There is a body of literature that I found related to this problem. The only issue is it tends to focus more on logistics companies, and a lot of the solutions are completely unsuitable for screeps because obviously we have very limited CPU power, so we need to make a good CPU efficient approximation for this in screeps. What are the features of the approximation that I'm making? Well, first of all, I'm going to account for the destinations of other trucks. That's quite important for me because I want trucks to fulfill requests in a certain region, especially if they're larger and able to do so, which of course comes to the environment of those requests, It counts for the ability of trucks to service a certain request. So, for example, a truck not carrying energy cannot fill extensions, whereas a truck, that has energy on it can fulfill those requests. And I also want to account for distance. The general principle I'm arguing for is it's better to go to a closer request and fulfill that than to travel further away if you can avoid it. Cool, so this is the overview of the algorithm, and don't worry, I'll be going step by step, so all of this will make sense. So first of all, there's a set of circumstances that we have that we're going to reset all the truck's destinations, and we do reset all of them simultaneously. At that point, I'm going to calculate a P matrix, what I'm calling a P matrix, which is basically a truck by request matrix, which each element of the matrix is how much or how badly does this truck want to do that job. I'm then going to perform successive column-row normalizations, and this basically serves to introduce what the other trucks prioritize to our P matrix. And then for the truck with the highest P value, I'm going to set its destination, and then I'm going to update requests and simulate the position and amounts from the truck we set the destination for, and repeat recalculating the matrix. So for example, truck 1 decides it's going to go to a particular extension. We treat it as if it's gone to that extension, and then we look, okay, now how is it prioritizing all the requests around it? So first of all, the P values. How are we calculating that? Obviously, we don't want this to be too costly because, we might have lots of rooms, and also we're trying to be as CPU efficient as possible. So it's a very simple equation. It's the priority for a given truck I to a request J is some priority value I multiplied by the minimum of the amount for the request, which could include empty. So for example, let's say it's picking up 50 energy. The requested amount would be 50 of empty, basically. Or alternatively, if it's like dropping off at an extension, it would be potentially 50 energy that it's requesting. So this would be like 50 energy in the truck. And then DJS is the amount that's being requested. So basically it's the minimum of the truck's amount or how much is being requested. This is divided by the distance, and for the distance, I'm actually just going to use the Chebyshev distance. I found this is a good enough approximation because you don't want to be calculating lots of path distances. Path distances are far more costly than just doing Chebyshev, which is the screeps distance, it's also called sometimes. And then we're also going to multiply it by the capacity of the truck. This acts as a normalization factor, and it also means basically that smaller trucks will have a higher priority overall to smaller jobs. So when do I reset the destinations? Because I mentioned, we reset under a certain set of circumstances. It's when a new request appears, a truck is created or it dies, and a truck arrives at its target destination. Alternatively, I also have a timer that I implemented. This is just for robustness. So for example, if you end up with lots of idle trucks, it's important to make sure you test and give them a job, but you don't want to be doing that every tick just because it'll be CPU inefficient, because remember, we're trying to be efficient with how we do this so we can run as many trucks doing as many requests as possible. So let's talk about these column row normalizations. So let's say we have our P matrix, so it's 3 trucks, 1, 2, 3, 4, 5, 6 destinations here, and we've calculated the P values for all of them. Note if the column or row sum is 0, obviously we don't divide by 0, we just leave it as 0. So we do a column normalization, then we do a row normalization. And then we can repeat that an n number of times. Now, we are not guaranteed convergence with this. This is because it's not a square matrix and there's also zeros in it, but yeah, it achieves the goal what we want. So for example, you can see that these trucks that had a priority of 1, they've both had their request decrease to that because they're both prioritizing that. Whereas some requests, for example, this one over here has gone up because number of trucks that are desperate to refill it is gone down. It is not that high, sorry. Cool. So I did forget to mention this step. I do apologize. We need to multiply element-wise with the original P matrix. And I will just talk about that briefly right now. And the reason for this is without multiplying by the original, you can get some really weird edge cases. So for example, consider a truck which is full of energy and another truck which is empty of energy. If you don't multiply by the original matrix, for the jobs they can fulfill, they'll all have the same value after those row column normalizations. This is because like the matrix will be, 0 always for one of them when the other one is not 0. So when you normalize that, it'll push it up and all the values will end up the same. So K is a constant that we can tune, and it's basically how important is the normalization result. So I found, for example, if you set a K of 1, you do get those weird behaviors, so it's important to have it lower. After we have done these normalizations and we've multiplied through by the original, by the way, don't look too much into these numbers, I've just kind of made them up. So in this case here, we are going to see, for example, truck 3 to destination 4 has the highest p-value after all of that, so we will set truck 3, destination 4, and then we will repeat simulating truck 3 as if it's gone to destination 4. And that's what I say, we recompute the p-matrix and we repeat. But yes, of course, trucks that already have a destination won't be given another destination, even if they have the highest p-value after all the recalculation. Hopefully that's, before we move on to the simulations, that's an indication of why we don't want to have to do this every tick or something, because doing that every tick will become quite expensive. So this is why we have those reset conditions wherein we will then recalculate the destinations. Okay, so let's do some simulations. We're going to remove the certain aspects of the game because we don't need to simulate the whole of screeps, and we're also going to remove parts of our algorithm so we can see the impact of them. I'm also going to, for example, test randomness with no randomness, and this is because I've previously talked a lot about why randomness can be important, and I won't spoil it for later. And I'll also show like different scenarios, so like, a very regular base, random requests, that kind of thing. Because when I first did a recording of this is something people talked about and mentioned as something I should have done. So what are the benefits of simulation? Obviously, I'm advocating that perhaps with certain aspects of the game, actually simulating it rather than trying to do it in screeps will be better. And the first is, of course, very fast feedback. So these simulations run very quickly, whereas, even on your own private server, if you're running like 10 ticks a second, that's still a lot slower than this. So this makes it a lot easier to collect statistics. Okay, scenarios. Here's 2 examples of scenarios I'm going to do. In the first one, I call it the extensions refill test. Both of these are on 50 by 50 grids. In the extensions refill, you have a central container, and my trucks have to pick up energy from that, and they have to go around to the different extension clusters of 5 that are placed randomly in each simulation run and fill them all up, basically. In the second one, we have random requests, which overall they all sum to 0, but they're just dotted around the place. Some are pickup requests, some are drop-off. The negatives are pickup, the positives are drop-off. Okay, so there are some differences obviously with screeps, but I don't think it matters too much. First of all, trucks can walk through each other and objects. I didn't think having collision was all that important for this. And all tiles are of cost 1 to move, and of course my trucks never actually die. There's no death mechanics or anything like that. So here's just an example of like how you can compare these sort of parameters. So what I have here is how many steps it took to complete the challenge between parameter set 1 and parameter set 2. And basically that line going through that diagonal is when they're both equal. And I can look how many points are above that line, which would mean parameter set 1 is better, and how many are below that line, which means parameter set 2 is better. And this is just one way of easily visualizing this data. I don't want to talk too much about this. Anyway, so the first test I'm going to do is, well, what happens if we get rid of the row column normalizations? Now, in these tests, I'm going to do the 2 extremes. We're going to have only using the row column normalization and not using it at all. I'm going to do 1,000 different runs, and I'm going to test it as I increase the number of trucks, we're going to have a capacity for 1,200 for the extension refill and a capacity of 3 for the random pickup and drop off because the requests are much smaller. Now, again, the reason I'm showing you this is just to give you an idea of like the sorts of simulations you could potentially run if you wanted to test like your logistics stuff. So here's some results. On the x-axis is the number of trucks, and on the y-axis is the number of steps we had to do on average to complete it. And what we saw is, first of all, the most important thing is just increasing the number of trucks. But then also, like, as you get to higher numbers of trucks, if you do it with the row column normalization, you end up finishing a lot faster than without. But yeah, like I said, we're not here to go into massive details on this. I'm just showing you like simulations in general here. And what I saw for the random pickup and drop off, though, is it was pretty similar, almost the same between the two, which, in hindsight kind of makes sense because with the random ones, it's sort of the environment is probably less important. So, for example, as I mentioned, the whole thing with the row column is it's like, if there's a cluster of requests, one truck can fulfill, only one truck will potentially go to that cluster because it's, aware of the spatial environment of requests, essentially. And just as a third one, someone very specifically requested that I do this, which is a regular set of extensions. So this is what they look like. And in that table there, we can see some results for when we have the normalization, and we use that to set the p-values, and when we don't have it at all. I did say I'd talk about randomness very briefly. I did find that it could make a run a lot better, but it could also make it worse. The spread was a lot higher, so I'm probably not going to use any sort of randomness when I use this in screeps, and I have tested it in screeps, and someone else very kindly has also helped me test it as well. And I found the performance, for example, was very sensitive to temperature, so anything above even the lowest temperatures, and it just sort of broke down, which, wasn't great. So I can't really advocate randomness if you want to copy this. And that's all. Thank you very much for listening. Please feel free to ask any questions. I'm happy to answer anything. And good luck with your logistics out there. Thank you very much.